The pressurized water reactor is the world's most common power reactor. It uses ordinary water for two jobs at once: slowing neutrons so the chain reaction stays efficient, and carrying heat away from the fuel. The water in the reactor is kept under very high pressure so it does not boil. That hot water flows through a steam generator, where it heats a separate water loop that turns to steam and spins a turbine. Keeping the loops separate helps contain radioactivity. A fun fact: most nuclear-powered submarines and aircraft carriers use reactors based on the PWR design. A boiling water reactor also uses ordinary water as both coolant and neutron slowdown material, but it works more directly than a PWR. Inside the reactor vessel, the water is allowed to boil, creating steam right around the fuel. That steam goes straight to the turbine to make electricity, then cools back into water and returns. The design uses fewer major parts because it skips the separate steam generator. One interesting fact is that BWR operators carefully control tiny steam bubbles in the core, because those bubbles naturally reduce the reaction rate and help stabilize the reactor. The pressurized heavy water reactor, best known through Canada's CANDU design, uses heavy water instead of ordinary water. Heavy water looks the same, but its hydrogen atoms are a heavier form called deuterium. That lets the reactor run on natural uranium, without the enrichment used by most other power reactors. Fuel sits in many pressure tubes rather than one big vessel, and the reactor can even be refueled while operating. A surprising fact: because of its flexible design, CANDU reactors have also been adapted to use recycled fuel from other reactor types, squeezing more energy from mined uranium. Gas-cooled reactors use a gas, not water, to carry heat away from the fuel. Britain built two famous kinds: Magnox and the more advanced HTGR, or Advanced Gas-Cooled Reactor. Both used graphite to slow neutrons, while carbon dioxide gas moved heat to steam generators that powered turbines. HTGRs ran at higher temperatures than water-cooled reactors, which helped efficiency. These designs are now rare, but they played a major role in the United Kingdom's electricity supply for decades. An interesting fact: HTGR fuel assemblies and graphite blocks gave these stations a very distinctive core layout, unlike most reactors elsewhere. The RBMK is a Soviet-designed reactor that uses graphite to slow neutrons and ordinary water to cool the fuel. Unlike most large power reactors, it uses many pressure tubes instead of one heavy steel vessel, and it can be refueled while running. That made it attractive for producing electricity on a huge scale. But the design also had serious flaws, especially in older versions, and it became infamous because Unit 4 at Chernobyl was an RBMK. After that disaster, surviving RBMK reactors received major safety upgrades, showing how reactor design details can matter enormously. High-temperature gas-cooled reactors use graphite to slow neutrons and usually helium gas to carry heat. Helium is useful because it does not easily become radioactive and stays chemically calm even at very high temperatures. The fuel is often packed into tiny coated particles designed to trap fission products. Some HTGRs use fuel blocks, while others use pebble-like fuel spheres. Because they can run hotter than water-cooled plants, they are attractive for making industrial heat as well as electricity. A neat fact: some designs are built so the core naturally cools itself enough to avoid fuel damage without active emergency systems. A Pebble Bed Reactor is a special kind of high-temperature gas-cooled reactor. Instead of long fuel rods, it uses thousands of tennis ball-sized graphite pebbles, each filled with tiny fuel particles sealed in strong ceramic-like coatings. Helium gas flows through the spaces between the pebbles and carries heat away. Fresh pebbles can be added and used ones removed over time, allowing a form of continuous fueling. The idea has been explored in Germany, China, and elsewhere. One surprising fact: a single pebble contains many thousands of miniature fuel particles, each acting like its own tiny containment system. A sodium-cooled fast reactor works differently from water reactors because it does not slow neutrons very much. Fast neutrons let it use fuel more completely, and even turn certain non-fuel materials into new fuel. Liquid sodium carries heat extremely well and stays liquid at high temperatures without needing high pressure, which is a big engineering advantage. But sodium also reacts strongly with air and water, so plants need special handling systems. An interesting fact: several countries built sodium fast reactors to test the idea of breeder reactors, which can produce more usable fuel than they consume. Lead-cooled fast reactors use molten lead, or sometimes a lead-bismuth mixture, to remove heat from the core while keeping neutrons fast. Lead has a very high boiling point, so the system can run at low pressure, reducing the risk of high-pressure accidents. It also does not react violently with air and water the way sodium does. On the downside, liquid lead is heavy and can be corrosive, so materials must be chosen carefully. A fascinating fact. The Soviet Union used lead-bismuth reactors in some submarines, proving the concept and demanding real-world service. A gas-cooled fast reactor combines two less common ideas: fast neutrons and gas coolings. Instead of water or liquid metal, it uses a gas such as helium to carry away heat, while the core is arranged so neutrons stay fast rather than being slowed down. In theory, that could allow high temperatures for efficient electricity production and useful industrial heat, while also making very good use of fuel. In practice, it is a difficult design to engineer and remains mostly in the research stage. One interesting fact: GFR concepts are part of several international plans for future advanced reactors. Molten salt reactors use hot liquid salt instead of ordinary water in the reactor system. In some designs, the salt only carries heat from solid fuel, but in others the fuel itself is dissolved in the salt. Because these salts can operate at very high temperatures without high pressure, the plant may be simpler in some ways than a water-cooled reactor. MSRs are still mostly experimental for power generation, but they attract attention for safety and efficiency ideas. A remarkable fact: the United States ran a molten salt test reactor at Oak Ridge National Laboratory in the 1960s. The Fluoride-Salt-Cooled high-temperature reactor is a hybrid idea that mixes features from two advanced families. It uses solid fuel, often similar to high-temperature gas reactor fuel, but cools the core with molten fluoride salt instead of helium. That salt can carry a lot of heat and run at high temperature without high pressure. The goal is to produce electricity efficiently, and possibly supply heat for industry too. This reactor type is still under development rather than widely deployed. A fun fact: researchers like FHRs, partly because they combine familiar coated particle fuel with a very different cooling approach. A supercritical water reactor uses water at such high pressure and temperature that it is no longer clearly a liquid or a gas. In that state, the water can carry heat very efficiently, which could simplify the power cycle and improve plant efficiency compared with today's light water reactors. Depending on the design, it may use ordinary water alone or combine water cooling with other core features. SCWRs are still conceptual or experimental, not commercial. An interesting fact: coal plants have long used supercritical steam technology, and reactor designers hope to borrow some of that efficiency for nuclear power. Small modular reactors are not one single reactor physics type, but an important modern category. They are built to produce less power than traditional large stations, and to be manufactured in factories as modules, then shipped to a site. Many SMRs are based on familiar designs like pressurized water reactors, while others use advanced coolants, such as molten salt, gas, or liquid metal. The main idea is to reduce construction risk and fit places that do not need giant plants. A surprising fact: some SMR designs are small enough to power remote regions, mines, or industrial sites. Microreactors are even smaller than most small modular reactors, designed for very low power output and easy transport. They are aimed at remote communities, military bases, disaster relief, research sites, or industrial locations far from large electric grids. Different designs exist, including gas-cooled, heat pipe-cooled, and liquid metal-cooled versions, but the common theme is compact size, long fuel life, and minimal on-site staffing. Most are still in development or early demonstration stages. One striking fact: some proposed microreactors are designed to be delivered by truck or aircraft container and run for years before refueling. Research reactors are built mainly for science, training, and making useful materials, not for large-scale electricity. They usually operate at much lower power than power reactors, but they produce strong neutron beams that scientists can use to study materials, test fuels, and create medical isotopes for cancer diagnosis and treatment. Their designs vary widely, from simple pool reactors to more advanced experimental systems. Because they serve laboratories and universities, they are often the reactors students first encounter. A surprising fact: many life-saving medical isotopes used in hospitals begin their journey inside research reactors, not power plants. Naval reactors are built to power submarines, aircraft carriers, and some icebreakers. Most are compact pressurized water reactors designed for reliability, long life, and the ability to operate for months without refueling or taking in oxygen like diesel engines must. They heat water into steam that drives turbines for propulsion and onboard electricity. Because space is tight and missions are demanding, naval reactor engineering focuses heavily on compactness and ruggedness. An interesting fact: nuclear submarines can stay underwater for far longer than crew supplies allow, making food and human endurance bigger limits than reactor fuel. A breeder reactor is defined by what it does more than by one exact layout. It is designed to create more usable fuel than it consumes by converting materials like uranium-238 or thorium into new fissile fuel during operation. Most breeder concepts use fast neutrons, which is why many sodium or lead-cooled fast reactors fall into this category. The appeal is huge. Far more energy can be extracted from mined resources. The challenge is complexity, cost, and fuel handling. A striking fact: if breeder systems were widely used, the energy available from uranium resources could last far longer than in today's once-through fuel cycle.